In this video, we learned how to find the equations of motion of a damped driven oscillator. And in particular, we're interested in the underdamped driven oscillator. In other words, an oscillator with a small enough damping coefficient to show some oscillation even if we don't drive it with an external force. And the big prize here is to find the resonant frequency of this damped oscillator. In other words, when we drive this thing with a sinusoidal force, we want to find the special driving frequency that maximizes the amplitude of the oscillations. And near the end of the video, we're also going to investigate how the relative size of the damping coefficient changes that resonant frequency. So, like all of our oscillator derivations, we begin with a force diagram so we can apply Newton's second law. In our diagram, the oscillator is currently below the equilibrium position, and remember, by convention, we're calling that a positive value of x, and at this particular moment, we also have a positive v, in other words, a downward velocity. Now remember, we showed that we don't have to worry about the force of gravity here. We already showed that the force of gravity cancels out of the force analysis when the spring settles to its equilibrium position after attaching the mass. So what forces do we care about? First, we can put in the spring force, and I'm just showing the magnitude of it there. So the magnitude of the spring force is given by k times x, and that's a restoring force pointing back to the equilibrium position. Next, we have our linear damping force with a magnitude of c times v, where c is some constant that we call the damping coefficient, and that opposes the direction of motion. So that's pointing up at the moment shown in the picture because the oscillator happens to be moving down at the moment we're showing in the picture. And finally, we have our external driving force F of t. And we're showing this as pointing in the positive direction at this particular moment of interest. So now we're going to apply Newton's second law. And of course, that's our old friend, net force equals mass times acceleration. And we can write it there in sigma notation. So now we're going to plug in all the force vectors on this mass using our sign convention to indicate direction. So that's negative for upward and positive for downward. So on the left side there is our net force, that's negative CV, again, because that's pointing in the upward direction, which by convention is negative. Similarly, we have a negative kx, and then we have a plus f of t because it points downward, and this all adds up to m times a. So now we can replace v with the time derivative of x and a with the second time derivative of x, and rearrange our equation with x and all its derivatives on one side. And there you have it, a second-order linear inhomogeneous equation describing the motion of our oscillator. So remember, we're particularly interested in driving this oscillator with a sinusoidal driving function and analyzing the long-run response of the motion. So we're going to say that our driving function, little f of t, is given by a force amplitude, big F, times the cosine of omega t, where we call that omega the driving frequency. Now, before we move on to solving this equation, here's an interesting point about the external driving force. We're actually driving this system using a small oscillating device at the top of the spring, not by directly exerting a force on the mass. So if this aggravates your inner skeptic, you're not alone in that. But the gist of the explanation here is that the device at the top is just changing the length of the spring a little as it oscillates, and that creates a time-dependent term in the spring force, which ultimately manifests as an extra force term in the Newton's second law analysis. It's completely equivalent to just imagining a direct sinusoidal force acting on the mass, but I wanted to be clear about the actual physical mechanism here. So now our job is to solve this inhomogeneous equation, and we approach this in the standard way. First, we find the homogeneous solution using an exponential proposal for x, and then we find the particular solution by using the method of undetermined coefficients, and then the general solution for the position function is the sum of the homogeneous and particular solutions. So first, the homogeneous solution. This means the solution to the equation with a 0 on the right-hand side. In other words, there's no driving function over there. So the standard solution here is to propose an exponential form for the position function, and we'll call that e to the rt, and then we run that through the differential equation, and the chain rule produces a factor of r each time we differentiate this function, and then we divide the e to the rt out of the entire thing. This results in what we call the characteristic equation. So I end up with the characteristic equation mr squared plus cr plus k is equal to 0, and then our challenge is to solve for r, and sub that back into the form e to the rt, and we've got our homogeneous solutions. And we apply the quadratic formula to solve for r here. So we have the negative of c plus or minus the square root of c squared minus 4mk, all divided by 2m. Now recall, we're interested in studying the underdamped oscillator in particular because that's where the phenomenon of resonance is going to occur. So we can assume that c squared is less than 4mk. And of course, this makes the interior of the square root negative, which is the whole origin of oscillatory behavior in an underdamped oscillator. So we can pull out a factor of square root -1, in other words, I, and we find that the solutions of the characteristic equation are negative c plus or minus I times the square root of 4mk minus c squared, just reversing the direction of the difference there, all divided by 2m. Now we recall that the real part of r corresponds to an exponential part of the solution, while the imaginary part results in sines and cosines via Euler's formula. So the end result is this. Our homogeneous solution has two linearly independent functions in it, and we're going to take an arbitrary linear combination of those. So we have arbitrary constants c1 and c2, and each one of these terms contains a decaying exponential piece, so e to the negative c over 2m times t, and then our first term has a cosine omega sub t times t. The second term has a sine function instead. Now I was just trying to clean things up a little by introducing that omega sub t. That's just the angular frequency of the oscillating part of these solutions. And as usual, that's just the imaginary part of the solutions that we got for the characteristic equation. Now the reason I called this omega sub t is because we're looking at what's called the transient solution of the equation. Note that each of these terms comes with a decaying exponential out in front, which means these terms die off to 0 in the large time limit. Now it's interesting to write this omega t in a slightly different way. We can relate it to the undamped oscillation frequency. Remember, that's square root of k over m, just the simple harmonic oscillator. So if I divide the 2m into this square root, that's like dividing by 4m squared inside the square root. So that first term inside the square root is just going to turn into a k over m, which we can then replace with the square of the undamped oscillation frequency. Meanwhile, that second term is going to be a c squared over 4m squared. So here's a really important point about what we're seeing here. The natural oscillation frequency of the underdamped undriven oscillator is not the same as the frequency of oscillation for the undamped oscillator. But we can say the oscillation frequency is close to the undamped oscillator frequency if we have a relatively small damping coefficient. In other words, if c is relatively small, what we're looking at is pretty close to omega naught. And again, we're going to call this the transient solution for our position function simply because it doesn't last very long. So now we move on to the particular solution of the equation, which, as it turns out, is the part that does continue forever, provided we keep driving the oscillator. So this is called the steady state solution. Now recall that the easiest technique we can use to find the particular solution is called the method of undetermined coefficients. And the idea here is to just propose a solution that has a general enough form to work when we run it through the inhomogeneous differential equation. So our proposal is going to be sines and cosines having the same frequency as the driving function. So that's omega. And the little a and b there, those are the undetermined coefficients. So we're going to run this solution through the differential equation and try to solve for the little a and the little b. Now we need to get the derivatives of this particular solution proposal in order to run it through the equation. So there's the first derivative. And of course, the derivative of cosine gives us negative sine. The derivative of sine gives us positive cosine. But notice that the chain rule produced a factor of omega out in front of each of those terms. Then we take another derivative. The chain rule produces another factor of omega. So now we have omega squareds out there. And now both terms have minus signs on them because on that second term, we had to differentiate a cosine function, which gave us the negative of a sine function. So we have the original proposed particular solution and the first and second derivatives. And now we're just going to throw these into the differential equation. There's what it looks like before we put the details in for these derivatives. And now we're going to put in the detail for x double prime. So my differential equation starts with an m times this huge expression for x double prime. That's negative a omega squared cosine omega t minus b omega squared sine omega t. Now we throw x prime in, and this time there's a c attached to that. So I have a c times the quantity negative a omega sine omega t plus b omega cosine omega t. And then finally we put in xp itself. So I get the term k times a cosine omega t plus b sine omega t. And then on the right side of the differential equation, we have that driving function big F times cosine omega t. Now the goal is to compare coefficients of the functions on the left and right sides of the equation here. So we're going to start by gathering all the terms that contain cosine omega t. So just doing some quick bookkeeping, here's a cosine term, here's another cosine term, and here's another cosine term. So that first one is going to be a negative am omega squared times the cosine function. The second one is c b omega times the cosine function. And the third one is k times a times the cosine function. And we're going to factor that cosine out of those terms as we go. So gathering all the cosine terms on the left-hand side, we have a cosine omega t times negative am omega squared plus bc omega plus a times k. And now we do a similar thing with the sine functions. There's a sine function here, and here, and here. And we're going to distribute into those parentheses and gather all those like terms and factor the sine function out. So this gives us sine omega t times the quantity negative bm omega squared minus ac omega plus bk. And there's the right-hand side of the differential equation still hanging out over there. That's f cosine omega t. So now we compare the coefficients of sine omega t and cosine omega t on the left and right sides of the equation. And the cosine omega t coefficient must be equal to f. Then when I look at the sine omega t coefficient, well, there is no sine omega t on the right-hand side, so that coefficient must be 0. So comparing coefficients has produced a system of two equations where the two unknowns are a and b. And we're going to attack this by using substitution. The easiest thing I can think to do here is to look at that second equation. It's nice and simple because it has a 0 on one side. And we're going to solve for a in terms of b. So all we have to do there is add this a term to both sides and then divide by its coefficient. In other words, the c omega part. And this gives us a equals b times the quantity k minus m omega squared, all divided by c omega. So now we're going to replace the a in the first equation with this new expression. And so we're multiplying that a by k minus m omega squared in that top equation. And this gives us a b times k minus m omega squared all squared, then divided by c omega. So there's that. Now to clean this up a little bit, we're going to multiply both sides by c omega. And that clears that first denominator. It also gives us a c omega squared on that second term, and it gives us a c omega on the right-hand side of the equation. And now, of course, we're going to factor the b out of the left-hand side and then divide by the coefficient of b. So there's our solution for little b. We get fc omega divided by k minus m omega squared all squared plus c omega all squared. And finally, we're going to take that b and sub it into our expression for a. And when I do this, the c omegas are going to cancel out. And we end up with little a equals big F times the quantity k minus m omega squared divided by that same denominator, k minus m omega squared all squared plus c omega all squared. So we found the values of a and b in the particular solution proposal. And now we're ready to put together the general solution. Remember, that's the sum of the homogeneous and particular solutions. So we've got the transient piece corresponding to the homogeneous solution. Remember, that has decaying exponentials. So whatever that contributes to the solution function, it's going to go away pretty quickly. And then we have the particular solution, which doesn't die off over time. So that's called the steady state solution. And just a reminder at the bottom here, the coefficients in that steady state solution are given by these two ugly expressions for a and b. So that's the general solution of the underdamped driven oscillator. But we're really interested in looking into the long-run frequency response of this oscillator. In other words, we want an expression for amplitude as a function of driving frequency. So we need to take a closer look at that steady state solution. So here's the steady state solution with coefficients of a and b on the cosine and sine parts. But it's not easy to see what the amplitude of this function is when we express it in this form. But we've already shown in a prior video that the sum of a sine and a cosine with the same frequency can be combined into a single cosine function with a phase shift. And I'm just going to outsource that derivation to a previous video I made on the harmonic oscillator, but the gist is that you use a trig identity for the cosine of a difference of angles, and you go from there to get the proof done. So I'll post a link to that video up at the top real quick. Now the whole point is that collapsing a sum of a sine and cosine into a single phase shifted cosine makes it really easy to see the amplitude of the function. That's just the big A out in front there. And it turns out to be the square root of the sum of the squares of our A and B. So it's the square root of A squared plus B squared. And when we sub in the details for A and B, remember, those are given by these terrible formulas. We should be able to simplify an expression for the total amplitude as a function of omega. So this really isn't as bad as it looks at first. Each of these denominators has the same factor. So when we square these terms, add them together and take the square root, we can just pull a factor of k minus m omega squared all squared plus c omega all squared out of that entire thing. And that just becomes the denominator of our combined expression. And it's similar for the common f in the two numerators. When you take the square root of the sum of the squares, you just factor the f squared out of the interior of the square root. It becomes an f on the exterior. So after factoring out all the stuff that's common to a and b, the only thing left inside the square root is this k minus m omega squared all squared. That's coming from the a term, plus c omega all squared. That came from the b term. Everything else has been factored out. There's the f in the numerator, and then the common denominator. So next, we notice all the stuff in the square root is the same as all the stuff in the denominator. So we can view it as all that stuff to the 1/2 power up there in the numerator, all that stuff to the first power in the denominator, and we simply use exponent rules to re-express this as all that stuff raised to the 1/2 power in the denominator. In other words, we can write it as a square root in the denominator. So there's an expression for the amplitude as a function of the driving frequency. It turns out to be big F. Remember, that was the force amplitude of the driving function. And it makes sense that amplitude is proportional to that guy. And then it's all divided by the square root of the quantity k minus m omega squared all squared plus the quantity c omega all squared. So there's the amplitude as a function of driving frequency, and now we can take a deeper look at the behavior of this function to get some more insight into the resonance behavior of our oscillator. So check out this plot of A as a function of omega for some particular choice of M, C, and K. We can see the amplitude of the steady state oscillations grows to a maximum value for one special driving frequency that we call omega sub r. So this is simple to do in the lab. You can just drive an oscillator at many different frequencies and search for the one special frequency that gives you the maximum amplitude of oscillations. But now, of course, we want to symbolically solve for this special frequency in terms of the parameters of our oscillator. In other words, the mass, the damping coefficient, and the spring constant. So to maximize this function, we need to minimize the denominator, which means minimizing the interior of the square root. So that's what we're actually going to apply calculus to. So we're taking the omega derivative of the inside of that square root and setting equal to 0. And that should give us a local minimum of that function, which then corresponds to a local maximum of amplitude with respect to driving frequency. So when we take this derivative, we have to use the chain rule on that first term. So I'm going to bring that power of 2 out in front of the whole thing, but then I have to multiply by the derivative of the interior, which is a negative 2m omega. So there's that negative 2m omega chain rule part of that first term. Then in the second term, when I differentiate c omega all squared with respect to omega, I get 2 times c times omega times the derivative of c omega, which is just another factor of c. So we have a 2c squared omega there. Now again, we're setting this all equal to 0 because we're looking for a local minimum of this function. Now in our next step, I did a few things all at once. First, I noticed there was a common factor of omega to both of these terms, so I just divided that out. Now what I'm ignoring here is the fact that that means omega equals 0 is one solution to this equation. And that's actually true, but it's just not the one that we're interested in. In fact, omega equals 0 must correspond to a local maximum of the function that we're differentiating, because in the graph, when I look at omega equals 0, in other words, driving this thing with no frequency at all, I see an amplitude local minimum there. And again, that's not really the part we're interested in studying, so I just canceled the thing out. Now, the other thing I did in this step was divide both terms by 2. So we had 2 factors of 2 in that original first term, and now we only have one of them, and instead of a 2c squared omega, in that second term, I've divided a 2 and an omega out, so all that's left there is a c squared. So next we'll divide by negative 2m and then add the c squared over 2m term to both sides. So that gets us here. Then we'll go ahead and solve for m omega squared. So I just visualize that by adding it to both sides, subtracting the c squared over 2m, and then flipping the whole equation around. And we get m omega squared is equal to k minus c squared over 2m. Now we can quickly divide both sides by m and then square root the result. And we arrive at this expression for the resonant frequency of this oscillator. So that's the special frequency that we have to drive it at to maximize the amplitude in the steady state solution. Now remember, we can view the k over m as the square of the frequency of the undamped oscillator. So we can call that omega naught squared, and we can write our resonant frequency as the square root of omega naught squared minus c squared over 2m squared. And this makes for an easy comparison to the previous result that we got for the transient solution. Remember, the frequency of oscillation for the undriven damped oscillator, in other words, the transient solution part, had a 4 down there in the denominator, but the resonant frequency has a 2. So this is a really common misconception about resonance. The resonant frequency is not the same as the natural frequency of the undriven oscillator. It is not the same as the natural frequency of the undamped oscillator, although all three of these omegas are going to be pretty close provided the c is relatively small. So our resonant frequency changes depending on the relative size of m, c, and k. And we want to do a graphical analysis showing how the resonant frequency, and in fact the entire resonance curve, change as the damping coefficient changes relative to m and k. So in the picture, we're looking at a plot of amplitude as a function of driving frequency. And note up here in the corner, we're putting a number on c squared over 4mk. And that's making reference to the interior of the square root in the characteristic equation. If c squared over 4mk is equal to 1, that's a critically damped oscillator. And of course, c squared over 4mk equals 0 is an undamped oscillator because c would have to be 0. So you might think we should run this animation as our parameter c squared over 4mk goes from 0 to 1, but that's surprisingly not quite right. So currently in the picture, c squared over 4mk is 0. Meaning the damping coefficient is 0, and we're looking at an undamped oscillator that's going to have infinite amplitude at omega naught, or square root k over m. So we're seeing that spike to infinity in the graph. But before we run the animation with c values increasing, we should look at the range of possible values of c squared over 4mk for which resonance will occur at all. And that means the interior of the square root in our expression for resonant frequency here better be bigger than 0. So we just write down omega naught squared minus c squared over 2m squared must be bigger than 0. And in fact, this omega naught is not serving us very well anymore. We're going to replace that with a k over m. And we go ahead and solve for c squared over 2m squared, reversing the direction of the inequality. So that's less than k over m. Now what we're trying to isolate here is c squared over 4mk. So we're going to divide both sides by 2 to get a 4 down there. We're going to multiply both sides by m, and we're going to divide both sides by k. And making all the appropriate cancellations there, we get that c squared over 4mk is less than 1/2. So it turns out that resonance no longer occurs when c squared over 4mk reaches 1/2. And this is actually pretty surprising. It means an oscillator could be underdamped and still incapable of exhibiting resonance. In other words, there would be no peak in the resonance curve if c is sufficiently large to push this parameter, c squared over 4mk, past 1/2. So as we run this animation, we're looking for two big qualitative points. So look at what's happening to the resonant frequency as the damping increases. The peak amplitude is occurring at smaller and smaller values of driving frequency as the damping increases, and the peak amplitude is smaller as the damping increases. In the next video, we'll apply our results for the underdamped driven oscillator to a couple common examples we might see in a physics or differential equations class. I'll post a link to that video at the upper left when it's done, and I'll see you there.